12.65, you're consuming power no matter what. And obviously that's where voltage drops, especially on the charging side, becomes more important. What I passed out was a set of tests that if you wrote these figures down, you would self-determine, truthfully, where your problems lie. So, I mean, it might sound a little interesting to be able to do a starter voltage test by putting your negative probe on the case of the battery, or on the case of the alternator, on a negative ground system. But if you went through each of these tests and did it exactly as it's laid out here, you'd have identified theoretically what problems you might have and why your battery isn't being charged. But there's more problem with undercharging batteries than there is on overcharging, frankly. And that by virtue of just the path problem and the starter. So when you start taking a starter motor, which are rated at roughly up to 700 amps you're pulling current on these starters. We tested every major starter manufacturer here this last month, and we tested a 42, we tested a 39 MT, we tested a Mitsubishi, we tested a Bosch, and we tested a Lee DeVille. And we're basically doing it on the same thing. What we figured out, you know, in terms of the starter draw, and why I get to the voltage drop in a minute, but the starter draw is pretty darn important, and you would think, okay, well, why am I putting this planetary on there? What's better about the planetary and why? And we wanted to know, from our point of view, how come they don't advertise it as drawing less current? In fact, that was the first time I'd heard a starter manufacturer tell them. Because when it comes down to technical data, KW rating is power consumed. So how do you say, well, my starter's better because it draws less current? Well, then it's only a 5 kW starter because that's power consumed, right? You with me? So the more power that the starter delivers is power consumed. But that all being said, if they're going to talk about how good their starters are, it doesn't matter whose they are, is what is the Newton meters and torque that starter delivers at a given RPM. So what we do is we take the starter apart, figure the ratios, control the shaft speed exactly, and record all of the power consumed, the torque in Newton meters, and the efficiency of the starter. In other words, how efficient is it power consumed versus power delivered? And that goes back into our grid, frankly, in our testing. But we've got a pretty state-of-the-art tester when it comes to be able to compare. And what we discovered is we think that there's a little bit of fabrication going on out there. So I want you to think about it when you see a rating on a starter that says 5.5 kW, which is what Mitsubishi rates theirs at, and maybe another one that says 7.5 kW. And then you look at the spec, and you look at what's written down in what we actually know by virtue of and the other problem you got is how much battery do you put behind it. And what we discovered is they got to be doing it with a 2 milliohm internal resistance application instead of testing them all at 4 milliohms or 6 milliohms, which basically is the size typically that your trucks are starting on with 331s. And then, of course, when you put a pure lead on, you're dropping that battery down to a 2 milliohm regardless. It's always better to provide higher cranking voltage than it is to provide less cranking voltage. And you say, well, Ohm's law would tell you that cranking voltage, or what you're cranking your starters at, is going to basically draw less current, less heat. Therefore, why would a slower starter be a problem? Well, from Ohm's law point of view, they're right. But from a practical point of view, what happens is your load stays the same, and your starter starts to turn slower, your armature is turning slower, and your path is increasing because the speed of the armature an EMF determines how much current you're delivering through that starter. So the problem becomes how much current is being consumed versus Newton meters of torque delivered. And it comes down to the fact that when you start increasing the power flow and you're only getting the same Newton meters of torque, you're consuming heat and energy, and you begin to melt the contacts in the solenoid. How many guys have started up their trucks only to discover that the starter's still engaged when they get done? Anybody have that problem? I hear it everywhere. I mean, I see it, right? We see it. We see starters coming in just smelling, simply because the contacts are welded. What is welding those contacts? Why is it causing that problem? And it's what's your answer? Too much heat, okay? Why are we developing that heat? I could tell you a couple of reasons. One reason is that if you allow your voltage to drop below SAE, which is 9.6 volts, you are now at risk with developing a starter to weld a contact and a failure. You're at risk. So why is your voltage dropping below 9.6 would be the question to ask. And you cannot do a starter test. You cannot do one if you do not measure the problem at the heart of the system, which is what is the battery's internal conductance, or what is the cold crank rating actually delivered through a carbon pile test to which is the best test for sealed product. Why are we not qualifying our batteries before we try and figure out, do we have a starter problem? Because you can't do it. If you can't deliver the current, you can't test the system. That simple. All right, so we get through the idea that the kW reading then is deliverable. So if we can deliver a better starter, always would be a starter that can deliver more current, more Newton meters in torque for less current. That'd be a plus. And there's few that actually do that. Most of them, if you go from a 42 and where you're looking at your power rating, it's interesting to see where it develops at what speed that power is developed. And these planetaries, in most cases, don't necessarily deliver better results for less heat. Some of them do. And that's hard for anybody to determine. Now, I bring this up only from the point of view is that if you say, okay, this is a 7.5 kW and that's what I need. And so you see a rating of a starter at 7.5 and you see another one at 5.5, don't think that that's necessarily what you need for that truck. And there's two reasons why. Some Japanese actually measure their current in JIS, or their kilowatt rating. What is power? Volts times amps is power. So you measure the voltage at the voltage that it drops to when delivering, and the amount of power it's delivered at that, or current. I times E, P equals I times E, current times voltage. That's simple. So if we can get current to be delivered at a higher torque rating at the speed required, that's the important part. And they've done that now, I believe now. And now the real advantage is, okay, what's the weight of it to put it in? And then what's the duration? How long is that thing gonna last? And that's what would be of importance, I think, is how long is that starter gonna last you? So if they're delivering power at less Newton, or more Newton meters for less current, that's pretty amazing as far as I'm concerned. So the key to it is we've got to keep our battery voltage up. How do we keep our voltage? When we slow the starter down, we increase the current flow through the hairpin, and the contacts weld. When the contacts weld, it's one of two things. Either the starter is drawing too much current because it's not manufactured correctly, or it's wore out, which is possible. It's just, that's likely that you got a starter that's wore out. That's a possibility. Or your voltage is too low because your batteries can't deliver the current. So why would it not be better to always be able to deliver more current to the system i.e. through the cables, i.e. through the battery's internal resistance, its ability to pass power, is going to save the life of your starter. On the other side of that equation, and probably the ones that maybe NEOP doesn't like as much, is the fact that an AGM battery or a pure lead battery also creates problems with immediate consumption. Now you're dealing with a battery, which is the heart of the system, right? That is consuming more power more quickly. So if the alternator is built and designed to deliver the power to handle that, then all power to it. Because now you got the best of both worlds. If the alternator can handle it, then great. And there's some people that think that that's the biggest problem with people putting AGM batteries in where flood came out. A lot of it is just poor design, whether it be in the original design or whether it just be in an alternator that's wore out, or whether it be the path that's now deteriorated over years of not having an adequate source. Now you got more heat and you get thermal runaway with bad path or connection problems, wire size not adequate. All right, so in measuring voltage drop, it's basically the difference between these two leads, between the positive and the ground lead in any series measured device. So we can measure the voltage drop, of which is entirely invalid if you do not load the circuit. So you can do that in a couple ways. Like you mentioned before, you can either use a carbon pile and draw down your battery, because remember, your battery is your worst load, period. It's what's going to take most of the consumption until it builds up its voltage and has a full state of charge. At that time, it's whatever the vehicle's loads are. But your battery becomes your biggest load and your biggest problem. That's why it's really better to not test the rest of the system so badly by having a battery that's undercharged, especially when you're replacing a problem. Get a charger on the batteries, bring them back up, so you're not overtaxing a brand new piece or one that's inadequate, if you will. Okay, so if we're measuring now on the negative side, and we can start moving these two leads, we can go from the negative battery connection, and nobody's probably got 30-foot leads in their voltmeter, so it's pretty difficult to necessarily be able to sometimes get to the ground on the starter, for example, or the ground at the battery where the truck's batteries are, and back up to, let's say, the alternator. But they do make long leads. It does make it, a little bit easier to test it in that form, one side at a time. So from, let's say, the negative connection of the post to the post itself, we load that circuit up with the carbon pile, or it'd be better if we turn up all the vehicle loads at this point as to what, or we crank while we test it, which would be the worst load. That's 1,000 amps right there. And they say you don't want more than 0.2 of a volt per side, or 0.4 is what SAE is, I believe. So you got 0.4 maximum. I think if you gave it 5, nobody's going to argue a whole lot in terms of total overall voltage drop. But you can measure that 0.1 per connection. So now we start moving. We can move now to our next test. And often it's going to take 2 people because somebody's got a twist on it if you're going to use the starter as your load. But even using the starter as your load for your voltage drop on your positive side is, that's what you're trying to measure, is how much drop do we have going on per side. But often you'll find that, well, I'll often get a call and say, I don't have any voltage drop whatsoever, or I have only 1/10 of a volt drop, or I only have a 0.5 of a volt, or 0.005. And more often than not, I'm thinking, they got to understand, if you cannot load that circuit, you're not testing that voltage drop. You have to turn your loads on. You got to load the wire up as much as you possibly can. It's like, how do you test an armature outside of a starter? I mean, how are you going to put 1,000 amps through a hairpin to see if you got an open bar? You're not. You're so much better off in the starter motor, drawing that 1,000 amps or 800 amps and then seeing what the pattern shows by virtue of ripple power, which, I mean, who's got those benches, right? Very few of us, to be able to do that. But it's the same thing. How do you load test and then check for your voltage drop? Because you really want to know. So now you move your leads to maybe your next point of connection. You can, if you do it from the negative post of the battery to the frame of the alternator, you've taken up every ground connection in the vehicle. Because now you got the aluminum going to the cast block, to the cable connection on the block, if there is one, to the negative cable on the back of the starter, maybe. But sometimes more of the blocks are isolated. But obviously, if you can find the ground connection on the back of the alternator, if it's an isolated ground, then you can pick that up. So now you're measuring your negative to the negative post, and let's say you've got 0.3 of a volt, okay? So now we're at 0.3 on the ground side, or 300 millivolts, okay, on your reading. And these little Medtronics voltmeters, by the way, are, we use this device more than we use anything else we use. Mostly because we can go around and measure current down to 10 milliamps, which for parasitics, ideal. And it's accurate within 20 milliamps, which is close enough for what we're trying to accomplish and understanding why our batteries are going flat, you know, or those shedding loads, whatever loads we might have. But then we measure the positive side, and we got 0.6 or 0.4 on the positive side. If you're measuring, you can still find out exactly where your consumption is by putting your meter. You can do it from like an alternator frame to the cast iron block while you're loaded and your alternator's at full output. And what you're measuring is the amount of resistance between the aluminum frame and the cast block. I had a Chevy Blazer one year when I was younger, and I had 0.7 of a volt drop on the ground side, and I couldn't find it until I pulled the bolt connecting the alternator to the block, and it's coated in cast, in corrosion. So whenever you run current through two dissimilar metals, you have electrolysis, which is different than just dissimilar corrosion. You're actually multiplying that corrosive path by 3 almost when you're building up that corrosion in electrolysis. Electrolysis when you run power through your dissimilar metals. That's why you would always be better to be able to bypass a ground circuit directly to the alternator, or wherever you mount your alternator, to make sure your ground path was as close to the alternator as possible, if not on the alternator or on the ground stud of the alternator. If you think about in a marine environment, just to give you an idea, you got cast iron rings, you got aluminum pistons, you've got whatever, and they isolate the grounds, because when you start putting 500 amps like you do through your fire trucks, you got real electrolysis issues going on if you do not have your grounds close to your alternator. And the advantage you have is immense in terms of the path. So we had a boat up in San Juan's running back and forth to Bellingham that had 2 large Cummins diesels on them, and they were going through engines every 18 months roughly, and it was running all day, every day. And the guys come out measuring the voltage and talking about zincs and the currents, eddy currents and all that, and the problems. And they said, well, here's what you got to do. You got to tie this engine with the other engine, and that will eliminate the problem. The problem then they had is they had 2 engines to replace every year. So we got involved in it. They brought us, they said, what can we do? We don't understand why we're going through piston and liners all the time on these diesels. And it come down to that they had grounded, negative ground case alternators, and they didn't have they had the grounds on the other side of the motor. So every bit of current that's come out of that positive cable is going around to the ground side of that alternator. It's coming back to the alternator where the power is being consumed. So you can imagine all this current, 130 amps or 20 amps are nonstop flowing all the time because it's running all day, 18 hours a day, was running through these dissimilar metals, creating electrolysis and taking the engines out. I think they ran the next set of engines 10 years before they touched them, just to give you an idea of the difference. How many times you've seen an emergency brake cable on a vehicle all heated up, or a transmission with a torque converter all pitted from a lack of an engine to frame ground that people have left off. When they put a new engine in, they forgot to put the bonding strap to the frame to the ground, same thing. All right, so now we got 0.4 of a volt on the negative side, right? Now we've got a total, because you can add it. All your resistance you measure in series can be added together to give you your total overall voltage drop. So at 400, you now have 0.7 volts drop on a 1.25, and now you've got roughly what, 0.45? Somewhere in that range, amount of voltage pushing current into the battery, and wonder why you can't get your batteries charged fully, and why it's so important to do voltage drop testing, and that you can take your voltmeter, whether it be the positive side or the ground side, it makes no difference, they're both paths, and where manufacturers would way rather not put a copper cable from the end of the truck to the other end of the truck to wherever the battery's at, they'd rather run it through the frame. So you got steel, you've got, anytime you weld on a piece of steel, you have a blockage of current flow. I remember a guy couldn't get his taillights working, and he was grounded right to the frame, no question. The lines of weld actually blocked the amount of current flowing through at that weld, which is surprising. So it's amazing what we see on the ground side and how much better you're off to run your grounds as close to your connections as possible. Any questions about voltage drop or why it's important?
On that boat example that you gave, was the fix to take the ground cable a little bit closer to the alternator? Is that what you were doing?
Actually, what we did is we went to an isolated ground alternator so that the block was out of the equation entirely.
Oh, okay.
So you can run back to the battery and ground.
Right, but the closer you get, if you could take that ground connection from the opposite side of the engine and move it to where the ground connected to the engine, if there were an engine ground. Why they put a non-ice, that's why most of your marine applications are all isolated grounds. Because you've got an environment where there's a lot of corrosion. And you can eliminate a lot of that, which is more electrolysis than anything. So running it right to the negative connection, so the output was a pure loop. No current going through the block at all. Eliminated the corrosion entirely.
Okay.
And on my DMs, I check for current in my coolant because it's tearing up radiators and things like that.
Yeah, that's been a problem on fire trucks, I've heard. Pierce? And I think they were having problems with don't they put a sensor in the radiator? I think they have some type of a sensor in the bottom of the radiator. You have some issue?
We've been asked by multiple OEMs for isolated ground alternators to prevent electrostatic discharge. They call it ESD, because they're seeing crankshafts getting pitted. Bearings going bad.
Yeah.
Those big haul trucks, big mining trucks, we have alternators on a lot of them. And they've asked us about isolated ground on those things. I think the problem is more so the 600 volt generators on the backside of that crankshaft. But they've asked us for isolated ground on our side. So yeah, we're seeing more demand for it, and Cummins is actually asking us about isolated ground units for regular road applications too. So you'll be seeing more of it.
Yeah, very important. Okay, there's one other issue, and then we're gonna get you started with me off here. And that is, we have with a lot of work, do a reverse engineering on everything that we build. And by that, we dimensionalize everything that we take apart, whether it's at the armature down to the wire turning gauge of the hairpin, down to the stator winding, to the ability to dimensionalize the ring that goes into the bell housing size, the drive at rest clearance to the flywheel, the amount of teeth, the diameter of the pinion, the number of teeth, the length of the starter, the solenoid position, which is, you guys are probably used to taking the starter off and calling up with exactly what came off of it and putting it back on. And I guess what we're capable of doing is determining what you want now, because we have normalized all that data. So you probably recognize too that a rotatable nose starter is not necessarily the way a starter comes out from the factory, because there are two drain tubes, or at least one drain tube in most of your 39s and your planetaries. These starters actually do develop more heat because they're light and lighter. So 42 MT weighs about, what, 68 pounds, something like that. So you've got a lot of mass to dissipate the heat. And so the advantage you might have, most people just don't want to install something that heavy anymore. I don't know what it is. Probably we're getting older. Anyway, aside from that, when we are mounting these things up, now we're able to, when people actually have to reclock, and are you aware that you can reclock starters to get your frame rail clearance, right? I noticed one time I'm out calling on an accountant. He says, I got the wrong starter, I can't get it in. Did you maybe move the nose? No, I didn't do that. It was on a different application, shall we say. But the problem with the rotatable concept is then you have to know where that drain tube is on that starter. Because what happens is obviously condensation, which is one of the biggest killers to starter motors. And that's why they put the drain tubes in them, so that they can allow the starter, which is now hot,